Okay, so any questions for me?
So question on number 7. I don't know if you see it.
What is number 7?
I have the.
You pick this one.
So, just like a quick clarification, it's pretty much number 6, but with the electric fields, or with it linearly polarized in the XZ plane.
Mm-hmm.
And in terms of the irradiance, would the irradiance, does it make sense that the irradiance would be the same as number 6's irradiance?
Well, it all gets back to that dot product.
Yeah, exactly. So, I mean,
And if the polarizations are in the same direction, like they were in 6, then you get the same result. If they're not in the same direction, then it won't be exactly the same result.
the math came out with them being the same, at least for me.
So they ended up having the same relative polarization. Like, it's a relative polarization. Well,
So, because they're propagating in slightly different, at slightly different angles, so the polarizations aren't really aligned, like they're not parallel with
Yeah.
each other.
So when you get the dot, when you have the dot product, then you get the cosine of the angle between them.
Yeah.
And if that angle is really small, cosine of really small is 1. But if it's not a really small angle, that's not going to be 1.
Okay.
wait, so we should get the same?
Very good.
Because I got the same.
Well, you'll see in the solutions next time.
So don't grade 7.
I thought you said do grade 7. I thought that's what this discussion was about.
While we're out, maybe don't grade 6. Or 8. Grade 4 and 5.
Or
Yeah.
just don't grade it for 2 days.
I know those cadmium layups. That's what it said. I knew that one.
Okay, so last time we talked about Twyman Green interferometer. And what's the takeaway for Twyman Green? System Michelson arranged to observe Fizeau fringes, and therefore it's good for measuring optical elements. Okay, we talked about the which one? Sagnac,
Max Zander? Is that Zander?
Mach-Zehnder.
Max Zander.
Okay, the Mach-Zehnder. And what's the takeaway for that? What do you typically use a Mach-Zehnder for?
Test tube modulation.
Yeah, usually it's a modulator.
Talk about the eye.
Yeah. Okay, then Sagnac interferometer.
Or gyroscope.
Gyroscope,
That's good,
rotation
yeah.
sensor. Okay, and then we talked about how to force polarization between orthogonal states. And what's the key component we use?
Polarizer 45.
45
Yeah.
Yeah. And then we talked about an example of its use in a Schumann interferometer, namely Nomarsky or DIC imaging mode in the microscope. Okay, so today what we want to do, now that we've talked about all of these two-beam interference topics, we want to move on. Yeah.
A quick question. So it makes sense if you're going between linear polarization states, put it at 45 degrees. Well, clockwise and counterclockwise, circular or orthogonal, what would a polarizer like that look like then?
So there, what one does is go back to the fact that we can take clockwise circular polarization, decompose it into two linear states, and counterclockwise, we can decompose it into two linear
And
states.
then just use linear polarizers?
Mhm.
Okay.
Yeah, and see how it works out.
Okay.
Yeah. And, yeah. That'd be the way to do it. Okay. Yeah, so with two-beam interference, we talked about how that works itself out with the electromagnetic model, with the scalar model. We looked at the fact that the two beams have to come from the same source. So we looked at division of wavefront, division of amplitude to get those two beams. We also then looked at ways we can have interference, namely Haidinger fringes or Fizeau fringes. And then we went through all the interferometers. So now what we want to do is an arbitrary number of beams, so n beam interference. And we'll approach it the same way. We'll first do the electromagnetic model. So that's going to be rather messy. And yet it will lead to kind of some simple results. And we'll do the scalar model. We'll get the same simple results, but much easier. And then we'll look at a phasor representation because it's a useful way to visualize what's going on. And then we'll start looking at some different scenarios. Division of amplitude, or rather division of wavefront. We'll take the 2-slit case and go to arbitrary number of slits. Then we'll go back to the slab, dielectric slab, and we'll take into account all the other multiply reflecting beams. And then that'll lead us into the whole thin film, Bragg mirror, anti-reflection coating arena, because it just plays right off of that. And then we can talk about ellipsometry and how you measure all these different quantities. And it'll also take us into Fabry-Perot's, which are just extremely useful. Depending upon time, we'll maybe look at some applications of that. So that's our game plan for the next couple of weeks. And remember, we don't meet next week. So we'll see you a week from Tuesday. Okay, so with n-beam interference then, we have some region of space where we have a bunch of different wave vectors representing propagation of plane waves. So we're going to assume plane waves in the electromagnetic model, and they're all of the same frequency. They're all mutually coherent. And what we want to do is figure out what the irradiance is in this space. And so to figure out the irradiance, we have to calculate the complex Poynting vector. To calculate the complex Poynting vector, we have to know what the fields are. So again, we start by writing down the fields. So we can write down the full complex representation of the ELF field as a complex amplitude vector times e to the j omega t, where since it's a plane wave, that complex amplitude vector has a very specific form. And remember the explicit spatial dependence, we usually suppress it. So we write it as E sub L. And then we can write that as some constant complex vector EL naught times e to the minus j k sub L dot r. So that then is our complex amplitude vector for this plane wave. And so we need to know what the total field is and the complex representation of the field in the region of overlap. And clearly that's just going to be the sum of all of the individual fields. So EL, E omega, J omega T. And then we can take this sum and write it as just the complex amplitude vector of the total electric field. And when we go to calculate the complex Poynting vector, that's 1/2 of the complex amplitude vector of the total electric field crossed into complex conjugate of the complex amplitude vector of the total magnetic field. So we just got this, which is that sum, and now we need this. So,
Real quickly.
Shouldn't there be a bar above
Yeah.
the EL?
oh yes, thank you very much. Perfect. Good. Okay, so we go back to the Maxwell equations for monochromatic waves, and using those we can end up writing that this has to be equal to j over mu naught omega times the curl of the total complex amplitude vector for the electric field. And so we can substitute in then for that u naught omega, substitute in for that complex amplitude vector, which is just sum L equals 1 to n of E sub L. And then in doing this curl, or actually we could rewrite it as J over mu naught omega. We can pull the sum out, L equals 1 to n, and have this be the sum of the curls of the complex amplitude vectors of the individual fields. So there's no reason why we can't reorder in that way.
That's because they're both just linear transformations, right?
Yep.
Okay.
Yep. And then we can write that as J over mu naught omega, sum L equal 1 to n. And when we work out that curl, we've done that before, we end up with minus J times the wave number K, UL hat crossed into EL. And remember K sub L over here, K sub L is the unit vector U sub L times the wave number K. So we have the wave number K here, unit vector U sub L in the direction of propagation. So you can work out that that's what you get. So then we have J times minus J, which gives us 1. And K over mu naught omega, we've already worked that out. That's just 1 over the impedance at the medium. And then we have sum L equal 1 to n of UL hat cross EL. And so that then is our expression for the complex amplitude vector of the total magnetic field. Okay, so now we're all set to calculate the complex Poynting vector. So complex Poynting vector then is 1/2, and this 1 over eta, I'm going to pull it out, so I have 1 over 2 times eta here, and then I have the total complex amplitude vector, which is the sum L equal 1 to n of E sub L. And then that is crossed with the complex conjugate of the total complex amplitude vector of the magnetic field here. And so we have the sum, and now I need to change the index for the sum because it's a different sum. So let's just use m. So m equals 1 to n, and then this would be u hat sub m cross b sub m. And then this is complex conjugated. The only thing that's complex is the e sub m, so complex conjugate that. Okay, so this is what we need to simplify. All right, so we can rewrite that as 1 over 2 times eta, and then these sums, we can pull them out. So we have the sum, L equals 1 to n, sum m equals 1 to n, and then we have E sub L crossed into um hat crossed into em complex conjugate. So that is our expression for the complex Poynting vector. Yeah, Carlos?
So maybe this is a dumb question, but wouldn't it be it almost seems to me like it'd be the same summation, because
Here?
yeah, it should be L, because the electric field of this one has a magnetic field of this one, so they're almost like.
So it turns out that this is the cross product between the total electric field and magnetic field complex amplitudes. And that this is the total magnetic field, complex amplitude, and this is the total, electric field. This is the total magnetic field, complex amplitude. And in order to properly do that cross product, we've got to have every term here and every term there. And if we make them the same index, then it's basically the same sum. So we're not counting everything we need to count if we make them the same sum. And you'll see in just a minute kind of how that works out. You'll see what we'd be throwing away if we did that. And we're basically throwing away all the interesting stuff if we do that. Okay, so at this point, we've got this double cross product. Let's plug in here this fact. So this complex amplitude vector, let's plug in the fact that it's this constant complex vector times the spatially dependent phase. So then we have sum L equals 1 to n, sum L equals 1 to n. And then I would end up with EL0 crossed into UM hat crossed into EM0 complex conjugate. So that's just picking off these pieces. Now I need to deal with this. And so I would have e to the minus j, k sub L minus k sub m dot r. And this, let's call delta k sub Lm. So that's k sub L minus k sub m. Okay, so this thing right here, we can use the back cab rule to expand it out. And if we do that, then that's going to be equal to UM hat crossed into, oh yeah, no, yeah, UM hat, or rather times, EL0 dotted into EM0 complex conjugate minus EM0 complex conjugate times EL0 dotted into UM hat. So that's what that's equal to. Okay. So that means I can rewrite this 1 over 2 times eta. Sum L equals 1 to n, sum m equals 1 to n. And then I've got this e to the minus j delta k sub Lm dot r. And then I have this term here, um hat. And then this, notice, well, let's just write it, EL0 dotted into EM0 complex conjugate minus, and then we have EM0 complex conjugate. I'm just going to reverse the order of that. So UM hat dotted into EL0. Okay, so that is my complex Poynting vector. Now, the thing that I want to do is notice we can kind of, this double sum, we can think of it in the following way. We can think of it in kind of like a matrix where I have L running this way and M running that way. And then basically for every value of L and M, that's one term here that I could put in a box,
I can add them all together.
and then you add them all together. Notice the diagonal here. That's when L is equal to M. When L is equal to M, delta KLM is 0. So this complex exponential just becomes 1. So I could pull out the L equal to M terms, in which case this is 1. This UM hat becomes UL hat, because L is equal to M. EL0, EM0 are the same. So EL0 magnitude squared. And then UL hat dotted into UL naught is 0 because,
Dot product 19 degree.
yeah, the electric field is orthogonal to the direction of propagation. So for the diagonal terms, I'm just left with that.
Which is your
Yeah, that's what it's going to work out to be. And then I have the rest of the terms, and I'll write it as L going from 1 to N, and then M not equal to L. And then we have e to the minus j, delta KLM dot R, and then we have, you know, the rest of this stuff. I'm just going to not bother rewriting it, but just use a shorthand. Okay, so that's about all we can do with it at this point. And then note that this is the complex Poynting vector, so if we take the real part of the complex Poynting vector, I'll write it down, is the time average of the real Poynting vector, or instantaneous Poynting vector. So by taking the real part of this thing, then I know what the time average power flow is. Okay, any questions so far? Just having fun with math, right? Okay. Now we want to look at special cases. So let's look at the special case where we have all of the beams are going in the same direction. They're all parallel. So if they're all parallel, and you look at this here, then notice this delta KLM goes to 0. So the complex exponential here goes to 1. And then this term, you know, if they're all in the same direction, then this dot product will go to 0. So all I'll be left with here is that term. So let's write it down. And notice this UM hat, it becomes just U hat. And then there's a U hat there, so I can pull that out. So I'm left with U hat over 2 times eta. And then I have the sum, L equals 1 to n, of EL0, magnitude squared, plus the sum, L equals 1 to n, sum m not equal to L. And then I just have this term over here. So that's going to be EL0 dotted into EM0 complex conjugate. Okay, that's fine. So basically, the first term is the diagonal set of terms. The second term is the off-diagonal set of terms. And notice on the off-diagonal set of terms, this one here would be E20 dotted into, or rather E10 dotted into E20 complex conjugate. And this one would be E20 dotted into E10 complex conjugate. These are the complex conjugates of each other. So basically everything over here, folding it over the diagonal, just is the complex conjugate. So I could rewrite this guy, u hat over 2 times eta, sum L equals 1 to n, EL 0, magnitude squared, plus sum L equals 1 to n, and then sum m equal to L plus 1 to n. In other words, I'm just going to sum over the upper triangle here of EL0 down to EM0, complex conjugate, and then I pick up the other term flipped over the diagonal by having EL0 complex conjugate dotted into EM0. Okay, you buy that? So if I rewrite that sum that way, I'm still picking up all the terms, but I'm only summing over the upper part of the matrix.
Those dots or?
Yeah, dot products.
There's still dot products.
Oh yeah, because they're vectors.
So this is still,
And O, and for double one.
this is still the answer for this special case, though. It's not a general.
Yes, it's for
Could you generalize
this
it?
case. Well, if that's not true, that term doesn't go to 0, and this doesn't go to 0, so we can't do that.
So we can't do just the half?
Yeah, actually, let's leave that aside and just focus on this guy. Okay, so why are we doing that? Well, we look at this guy, that's 2 times the real part of EL0 dot EM0 complex conjugate. So, that simplifies things. Now let's say we want the radiance in a plane orthogonal to the direction of propagation. Then that plane has a surface normal that is u hat. So the irradiance is always the magnitude of the real part of the complex Poynting vector dotted into the surface normal of whatever surface we're calculating the irradiance over. And so here we're saying plane perpendicular to direction of propagation, so n hat is u hat in this case. We've got a u hat out here, we take the dot product, that's 1. And so what we end up with is the sum, L equals 1 to n, of EL0, magnitude squared over 2 times eta, plus this double sum over here. So we have the 2 here and the 2 here cancel, so that gives us a 1 over eta. Sum L equals 1 to n, sum m equal to L plus 1 to n, and then we have the real part of EL0 dot EM0 complex conjugate. And then we look at that first term and we say, hey, that's just the sum of the irradiances of the individual beams. And so this second term must be the interference term, call it J sub n. So if we have a bunch of co-propagating beams, then the irradiance in a plane perpendicular to the direction of propagation is just the sum of the individual irradiances and this interference term. And then notice if n equals 2, then the first one just becomes I1 plus I2. And then it's basically just this 2 by 2 matrix here. And so that double sum just gives me these terms. And that ends up being the interference term that we had before for the two-beam case, which is what this becomes when n is equal to 2.
What is that subscript on the J over there that you?
Sub n, capital N. Okay. So, we have a general result for the collinearly propagating case that reduces to what we got for the two-beam interference case. Now, let's do a little example. Let's say that we have n beams all propagating in the z direction. And let's also say that they all have linear polarization in the x-hat direction. And we want to know the irradiance in a plane perpendicular to the direction of propagation, so in other words, in the xy plane. Then what do? Well, same thing we did before. Write down the fields, calculate some of the gradiences, calculate the interference term, add them together, and we're done. So we need to write down the fields. So let's write down this constant complex vector EL naught. And in general, I mean, it just represents the amplitude, so let's call it A sub L. And the phase, let's call that phi sub L. And then the polarization state, which is x hat. So we just wrote down the fields. That's not too bad. And now, the irradiances, IL, well, that's just going to be AL squared over 2 times eta. So that's not too bad. So we then need the interference term. So let's just write down the whole thing. The irradiance is sum L equals 1 to n of I sub L plus sum L equals 1 to n, sum m equal to L plus 1 to n of, let's see, we have 1 over eta out front, and then we have the real part of this dot product, which gives us an AL AM cosine EL minus EM. Because it's the real part of e to the j phi L times e to the minus j phi M. because of this complex conjugate. And the real part of that is just cosine. So we can rewrite this, sum L equals 1 to n, I sub L plus, and then let's convert these into irradiances, so that means I need a 2 out front, sum L equal 1 to n, sum m equal L plus 1 to n, square root, I sub L, I sub m, cosine, d sub L, d sub m. That looks kind of familiar. As kind of a obvious generalization of the two-beam interference case. Okay. So, generally speaking, anytime we have many beams that are collinearly propagating and have the same polarization state, that's always what we come up with. Now, let's look at a special case of this. Namely, let's say that I sub L is just equal to I1. So they all have the same irradiance. Then, in that case, the irradiance is just going to be n times I1 for that first sum. And then we'll have plus 2 times I1. And then we'll have this double sum, sum m, or L rather, L equals 1 to n, sum m equals L plus 1 to n, and then we have the cosine of VL minus VL. Okay. Fine. Now let's do a special case of that special case. Let's say that VL minus VM is 0 for all L and M, meaning they'll have the same phase. Which is the same thing as we have, as saying we have complete constructive interference of all the beams. Then in that case, this cosine is just a 1 for every term. So this double sum just counts up the number of terms we have. How many terms we have is the number of slots in this upper diagonal here, the upper part above the diagonal. And so that means we have I is equal to n, I1 from the first part, and then we have plus 2 I1 times the number of spots there, and the number of spots is n squared minus n over 2, because n squared is the total number of locations here, right? Subtract off the diagonal, that's n, so that's n squared minus n, and then we're just taking the upper half divided by 2. Okay, so when we add this to that, we just get n squared I1. Which is kind of what you'd expect. Okay, so what this is saying is that collinearly propagating beams are radiants in the plane orthogonal to the direction of propagation. They're all the same irradiance and they're all in phase, so I get constructive interference. And the total irradiance is the square of the number of beams times the individual irradiance. So if I have 100 beams, I have 10,000 times the irradiance of a single beam. That's a nice boost. Okay, and then we have to worry about energy conservation. You'll see how that works out. You never violate it. Okay, if n is 2, then of course that total radiance is 4 times R1, which is what we saw for the tubing case. Okay, any questions? We exhausted? Mentally zombified?
No way.
Yeah, we've got more. Okay. So that is the electromagnetic model approach to M-beam interference. And, you know, it's no big deal. It's just complex Poynting vector, write down the field, and a bunch of algebra. So, not that big of a deal. Let's see what happens if we worry about scalar waves. So, we'll use the scalar model, and we're going to and beams all the same frequency. And then you'll remember that, well, so same frequency, which means it's monochromatic. So that means that for any given beam, the complex representation of the field is just a complex amplitude times E to the J omega t for any beam. So this is, let's just say we start with the single beam case. And then the irradiance is just magnitude squared of the complex amplitude, which is what we saw for the scalar model. So then if we do n beams, then we have that the complex representation of the field, and now this is for the total field, is clearly just going to be the sum over all of the individual fields. So let's say L equals 1 to n, and then we'll have the complex amplitude of the Lth beam times E to the J omega t. That's the complex representation for the Lth beam. And so we can pull out the E to the J omega t, and we just have the sum of the complex amplitudes. So evidently the complex amplitude of the total total beam or total field is just the sum of the individual complex amplitudes, which is what we would expect. Okay, so we can calculate the irradiance then as just magnitude squared of this complex amplitude. And that means we've got magnitude squared of the sum L equals 1 to n of u sub L of r. And so we plug in, and that's going to be sum L equals 1 to n sum m equals 1 to n of UL UM complex conjugate, where I'm doing the usual thing where I'm taking this complex amplitude, making the spatial dependence implicit, so I'm just writing it as a u sub L. So if I follow exactly what I did over here for the electromagnetic model, I'm going to skip all that, but it's the same steps. Then if I pull out the on-diagonal terms, L equals 1 to n, what I end up with is I sub L, and then all the other terms, I end up with L equals 1 to n, sum of m not equal to L. Or actually, I'm just going to jump right to it. So m equals L plus 1 to n. Then I'll end up with UL complex conjugate plus UL complex conjugate UM. And we see that that is 2 times the real part of UL UM complex conjugate. Which sure looks familiar, just like over there. And we got there a whole lot quicker. Okay, so at this point, I mean, we basically have this result, or the equivalent of this result for the electromagnetic case in the scalar model. Yeah.
Just to make sure I understand, in the scalar model, we also have to assume they're going in the same direction.
No, actually we don't. They have to be paraxial.
Okay, yeah, yeah.
So, yeah, they can be going slightly different directions, but only slightly.
Okay.
And also, they have to have the same polarization. So this, the only time we can use scalar model is if we have periaxial beams and all of them have the same polarization. That's our condition for using the scalar model. Okay, so at this point, we could do the same set of examples over there in the scalar model. We could say, okay, let's have plane waves, and let's say that they're propagating in the z direction, and then we could write down the individual fields, and bottom line is we end up with exactly the same result. So I won't bother doing it. I'll let you do it.
So it's a homework problem?
Yeah, it's an optional homework problem.
My favorite kind of homework problem.
Yeah,
Those are the ones I always have time for.
Yeah, that's right. Yeah. But at any rate, getting to here, since it's the same functional form, we're obviously going to get the same result. So scalar model is a heck of a lot easier to work with. So if we have paraxial beams, same polarization state, man, we want to go. It's just easier. Although on the electromagnetic model, we already did all the hard work, so it's almost just as easy. Okay, great. Any questions? No? Still stupefied? Okay.
So, since this has to be coherent, they're all coming from the same source, right?
Mm-hmm. Yes.
So, I guess, are we going to do the whole power thing?
Oh, yeah, yeah, yeah. And we need to do the power thing in the context of specific cases. Because what we're going to see is that when we have division of wavefront, the power gets resolved in one way. When we have division of amplitude, the power gets resolved in a different but related way. So we need some specific examples of cases. Okay, good deal then. Now what we want to do is look at an alternate way to think about the scalar model. Namely, we want to look at phasor diagrams. As soon as we say phasors, what do you think?
Star Trek.
Star Trek, not that kind of phaser. What do you think? Unit circle?
RLC
Funny
circuits.
RLC circuits, funny math.
Angles. Yeah.
So phasor diagrams are always about how you plot a complex number in a complex plane. Always. So if we look at this relationship right here, U total is equal to the sum of U sub L, where I've made the spatial dependence implicit. If we look at a specific point in space, then the ULs are just a set of complex numbers that add together to give us some other complex number. That's all it is.
Did you make the assumption that they're all parallel?
No, no assumption at all. Other than this, to be able to use the scalar model. So, at any particular point in space, this is just some complex number. Therefore, we can write this upon the complex plane. So, let's be specific about it. UL then is going to have some amplitude, call it UL naught, and some phase, phi sub L. So that's the complex number. Has an amplitude and a phase. So that means that this sum is just U10 e to the j phi 1 plus U20 e to the j phi 2 plus et cetera, UN0 e to the j phi n. So it's just some sum of complex numbers. Therefore, we can use phasors to visually see what's going on. So let's let n equal to 3 just to make this manageable. And I have the complex plane, real axis, imaginary axis. And let's say that this first complex number is that point right there. Then that point is a distance, U10, away from the origin at an angle, V1. And when I add the next one to it, all I'm doing is starting from that point, going a distance U20 at an angle phi 2, and then that's going to give me a point that's the sum of those two numbers.
Is V2 relative to like a U1?
It's relative to the positive real axis.
Okay, it's relative to the real axis. Okay. Gotcha.
And then let's say I got n equals 3, so I've just got one more here. Let's say that takes me over here. So this is U30, and this is the phase phi3, so that takes me to that point. And so when I add these three complex numbers, I get to that point in the complex plane. And clearly, that's going to be a distance, U tot, 0, from the origin at an angle, call it capital phi. So I can think of interference then at some point in space as just the sum of some complex numbers, which I can visualize as kind of the vector sum of some phasors. Questions?
Sorry, this is a scalar model question. Is there not a e to the kr in the?
So all we've said is they all have the same frequency. So they're monochromatic. We haven't said whether they're plane waves or something else.
Okay.
So that means then for an individual wave, it'll have this form. It's monochromatic. It has some complex amplitude, whatever it is. It's dependent on spatial position. If I pick a specific spatial position, then that's just some point in space,
In that case.
and this just becomes a complex number. Now, if it's a plane wave, this thing has the functional form of some complex number times e to the minus j k dot r. And if I pick r, then this thing is just some complex number. Multiplied by that complex number, so the whole thing is just some complex number. And that's basically what we're saying this is, it's some complex number. If this was a paraboloidal wave, well, it had a different functional relationship. But still, at a point in space, the complex amplitude is just a complex number. So this formulation still holds. Okay. So, if we have constructive interference, then by definition, all of the phases are the same. And so if I draw that out in the complex plane, then that means the first beam, the U10 at that phase angle, phi, and then I add to it the next one, but it's at the same phase angle, so it goes off in the same direction, U20. And let's say I'm looking at n equal 3 again, just so it's easy to draw. And that third one, again, same phase angle, so U30. So it just goes in a straight line radially from the origin. That would be constructive interference. And then this distance here would be the amplitude of the interfering wave, and this angle is just phi. So in the phasor view of the scalar model, when we have constructive interference, that's pretty much what it looks like. On the other hand, if we have destructive interference, and again, let's just do n equal 3. We have the first beam, U10, some angle phi1, and then we have the second beam, say U20, at an angle phi2, and then the third beam takes us right back to the origin, U30, at an angle phi3. And so when we sum them together, we end up back at the origin, so we have no field, therefore no irradiance. We have destructive interference. So the phasor model then is nice in terms of just visualizing how the interference goes. So you will have a homework problem on visualizing interference using a phasor diagram. Okay, any questions? We're good? Pounded into mental mush?
So kind of a question. So in this last case of the destructive interference, so they're going to sum always to just like 180 or to 0, yeah. But
Yeah.
does that mean like whatever your n is, each individual one is just that over n?
Well,
Or like 1, 3, 2,
so
0,
so what I've drawn here is a triangle,
yeah.
and so those angles have to sum to a particular value. Yeah. But if I have n equals to 7, then you can kind of work it out and see what they have to sum to.
Okay.
Yeah, but that would be an interesting thing to look at. Okay. Yeah.
So this looks like it's much more likely to have destructive interference than constructive interference, given just any number set of beams.
Yeah, you only get constructive interference in a very particular situation. namely they all have the same phase. And if you have some process that leads to a variety of different phases, then the probability of them all having the same phase becomes rare. And hold that thought, because that's going to lead to an interesting phenomena that's characteristic of multiple beam interference. And I'll point that phenomena out when we get to it. Okay, so we ready to do an example? Or do we just want to call it a day? I think we should do an example. Okay, so let's do a division of wavefront situation. And let's draw our coordinate system. And let's do X there. It's a lot of space. And I'm doing that deliberately so you don't run out of room. Let's say that we have an opaque screen over here. And it looks something like this. And I've got 4 slits. So slit 1, slit 2, slit 3, slit 4. And then, the distance between slits here, let's say is D for all of them. And then let's say that from the left, I've got a plane wave incident. And then the plane wave, when it comes to the slit causes it to diffract. And so I just have these cylindrical waves diffracted into the slits. And then let's stick a cylindrical lens here. And let's look in the back focal plane of that lens. So with a lens then, all the rays that enter at a given angle will be focused down to a particular position. So that means let's take a look at all of the rays going at some angle to the z-axis, like this. So this is theta for all of them. Then they're all going to focus down to the same point over here. And clearly at that point we're going to get interference between the light from each of the rays. And let's say that that position is X. And so if we draw from the center of the lens X, that angle is going to be theta. Same angle as this. Because a ray that goes through the center of the lens is undeviated. So you have the angle theta there. And let's say that X is much less than the focal length. So we can say that theta, which is the arc tangent of X over F, is going to be about X over F. So in other words, theta is small, so we can make that approximation. Okay, so so let's go through the thought process again as applied to this end slit example. So first of all, which model do we want to use to figure out what the irradiance is over here on the observation plane?
We haven't made any assumptions about polarization.
Well, we haven't said anything.
We'll go with the electromagnetic model.
Okay, and then why?
How small is D?
How small is D? It's just something.
Is that wave characterized by anything? So like, it's plane wave?
Yeah, all I said was plane wave. So it has to have some polarization, right? So, you want to pick a polarization?
Why?
Okay, what do you want to pick?
Why?
Y hat? Okay, I'll go for that. Y hat. Okay, so we have Y hat polarized light here. And what's the polarization state going to be over here? Y hat. Okay, I'll apply that. So Y hat on everywhere. So same polarization state. So what model you want to use? Scalar. What about paraxial?
Close enough.
We just made the paraxial approximation right there. Okay. So same polarization, paraxial, yeah, scalar model. Okay, so at what point do we want to calculate the irradiance? Clearly at x, right? Yeah. So we could now say, well, let's write down the fields at x. Okay, I'll bite on that. So what's the field at x for the beam that goes through slit 1? Do we want to use E, scalar model? How about let's just do an A?
Oh, A, yeah.
Just
A
to
one.
pick
Okay.
something easy. Okay, and so that's the amplitude. What else does it have?
Polarization.
No.
Oh, wait.
Yeah, we're doing the scalar model, so that's already subsumed in the model.
Time dependent.
Okay, what's U1? So,
Phase offset, I guess.
So it's just a phase, right?
yeah, it'll be an amplitude, and it'll be a phase. That's the complex number for the complex amplitude of the field right here. So remember, the complex representation of the full field is this, right?
Oh, it's already picked up.
Yeah.
So we're just worrying about the complex amplitude here.
Okay.
And we determined the R, so we don't need it.
Yeah, R is fixed, it's
Yeah, R
that
is
point
fixed.
right there.
Yeah.
So at that point, the scalar complex amplitude is just some complex number. What does that complex number embody in terms of information? It embodies the amplitude and the phase. Okay? So what about the field or the complex amplitude of the field for the light that goes through slit 2? A2, so amplitude, e to the j phi2. Okay, is there a relationship between phi2 and phi1? So the phase right here and the phase right here, are they different?
No.
Nope, same. Okay, so if I go here and I propagate back along this line to there, then basically phi1 is whatever the phase is there plus however much phase I pick up propagating that distance, right?
Yep.
Okay, so the phase right here is the same as the phase right there, so that piece of phi 2 is the same as phi 1. And then if I travel from here all the way back over here, yeah, the phase I pick up is different than if I do path 1, but it's only different by that much right there. Call that delta S.
That's right, same page about goes to
Because that's what a lens does, right? Takes something that's a wavefront here, which is orthogonal to these rays, and it's the same distance on any piece of that wavefront following a ray over to X. That's what a lens does. So, evidently, phi 2 is just phi 1 plus what? 2 pi over lambda naught times the refractive index times delta S. Right? Because it's the optical path, which is refractive index times physical path. And then we have to turn it to a phase using 2 pi over lambda naught. Are we good with that? Okay. So that means I could write here P1 e to the j. Oh, and is this plus or minus? Plus. Minus.
accumulation position.
Because
Oh, that's right.
as we propagate positive
We lose
distance, we
phase.
pick up negative phase.
Yeah.
Okay, so we have e to the minus j, 2 pi over lambda naught and delta S. Okay. All right, so now, U3. What's the complex number going to be that represents the complex amplitude of the field for light going through slit 3, traveling that path? So some amplitude, K3, you'll have e to the j phi 1, that's the same. And then here, if I go over here, then basically I pick up a delta S there and a delta S there. So I'll have minus j 2 pi over lambda naught n delta S times 2. Okay, and then U4. K4, e to the j, V1, e to the minus j, 2 pi over lambda naught, and delta S times 3. Okay, I'll buy that. So, these amplitudes, do you expect them to be different?
Depends on the material, I guess. They'll probably different distances.
Did we say anything about the widths of this?
No, we just said they're small. So we get diffraction. So we get the same diffraction for
Same
each
fraction.
each slit. And the only difference in path is these little tiny delta S's. So to first order, they're the same amplitude. Wow. Okay, so that means U total sum L equals 1 to n of U sub L, which is sum, well, we can pull the A's out. A sum L equals 1 to n of e to the minus j L 2 pi, actually it's going to have to be L minus 1, 2 pi over lambda naught n delta S. Right, it has to be L minus 1 because when L is 1, you get 0. So I could rewrite that as A sum M equals 0 to 3. This this n is 4 here. E to the minus j, m, 2 pi over lambda naught n delta s. And then delta s over here, notice the delta s, you know, if this is theta, then this is theta here. This is d. So delta s is what? D sine theta. Theta is x over f, it's small, so this is essentially x over f times d. So over here, this delta s is xd over f. Okay, so we're all ready for the punchline, and we're out of time, so we'll have to save the punchline until a week from Tuesday, after we've had all Thanksgiving, to forget this. It's a long time to be held in suspense, huh?
Yeah.
What will we do?
Yes. It'll be bugging me the entire time. Okay, so we'll pick it up here a week from Tuesday, and we'll see, I mean, we're just right at the point where we can say how all this works out. And we'll pick up some really important behaviors of multiple beam interference by looking at these.